Okay, so zoom out a little bit there. Here's where we left off last time. I found 2 of the 6 arrangements for our integral that we wanted to evaluate. I went ahead and just worked out the remaining 4 just because I spend more time writing than I really want to spend on these videos. So what I did here is I took this second region D, which is it's a projection of our solid into the x and y, or sorry, the xy plane, which means my inner integral should be with respect to z. And to find the bounds on z, remember we're looking at a surface on top and a surface on bottom that bounds this solid here. Well, the top can be thought of as the top half of this cylinder, and the bottom can be thought of the bottom half of this cylinder, where the cylinder is given by this equation right here. So if I solved this for z, I would get, it's kind of small here, but positive square root of 9 minus y squared for my upper limit, negative square root of 9 minus y squared for my lower limit. Those are the limits of integration when I integrate with respect to z. Integrating with respect to x and y are simply a matter of looking at the restrictions on x and y in this diagram. Because I have a rectangle here, both of those are going to look like intervals. For x, it's the interval from -2 to 2, which you can see. For y, it's the interval from -3 to 3. If I wanted to still stick within this region, but switch the order of my 2 outer integrals, notice because I'm in the xy plane, my inner integral still needs to be with respect to z, but I can switch these two, and I don't, because it's a rectangular region, I don't have to rethink the limits of integration anymore. I just swap the original 2. That's the benefit of working with rectangles. This region is very, very similar. Notice the only difference between what we have here and what we have for these 2 integrals and what we have for these 2 integrals is that the y's here changed into z's here. And again, that's just because my integration on the inner integral is done with respect to y instead of z. So when finding the bounds on this cylinder up here, I'm solving for y instead of solving for z. That's really the only difference. So that's it for that one. Let's go ahead and move on to the last couple of things we need to talk about, some applications of triple integrals. The applications that we talk about here are basically the analogs of what we've already talked about as far as applications for double integrals. With double integrals, we showed that if you have a region D that you're integrating over, and you make your integrand dA, this is a dV, but back in double integrals it was dA, or 1 dA. We show that the result of that integral comes out to exactly the area of the region that you integrated over. You can show with a similar argument that if you integrate just the function 1 dV, or I'm not even going to write the 1, just call it dV, over a solid E, the result is the volume of that solid. Very similar reasoning as what we did with that double integral application to area. So this is similar result to what we talked about before with double integrals. Like I said, I want to work through an example here. In this case, we're going to try and find the volume of the solid enclosed by these 2 paraboloids. I want to start by graphing those 2 surfaces, those 2 paraboloids. We're going to see that the only portion of these paraboloids that are going to matter for us are going to be to the left, or sorry, not to the left, to the right of my xz plane, so I'm not going to worry about what's happening to the right. I'm sorry, to the left. I'm getting my left and my right mixed up here. Okay. So this first paraboloid here, y equals x squared plus z squared. Remember, the best way to graph this is to look at for traces of this. So if I look for a trace, for example, on the yz plane, let's label these z, y, x. Okay, so for a trace in the yz plane, plug a 0 in for x, and I get y equals z squared. So that's going to so hold on, let me see, make sure I got the right thing graphed here. Yeah. Y equals z squared is going to be a parabola that looks kind of like this. Now in this case, I'm not going to be super careful with my labels on my axes because I kind of just want to get a general picture of this thing first, and then I can be a little bit more accurate from there when I start looking at projections. So next up, I'm going to look for a trace of this paraboloid in the xy plane. So that means plug a 0 in for z. I get y equals x squared. It's going to look like a parabola in the xz plane. And so my paraboloid is going to look, let's make this come out a little bit further, kind of like this. Okay? And it's going to obviously continue onwards, but I have a second paraboloid here, which if I were to graph the traces of this paraboloid, you're going to find that they have intercepts, or a y-intercept of 8, and the parabolas are going to meet the one that we already drew in this circle here, where the y-coordinate of the y-coordinate here where they meet is 4. Okay, I'm going to let you kind of come up with this. You kind of get this sort of football-looking shape. And again, the goal here is to find the volume of this. This is not an ellipsoid. It looks kind of like an ellipsoid, but it's not. So we need to be careful with how we come up with this volume. What I want to do is set up a triple integral using this little formula here. And in order to do that, this is our region E. I need to determine what kind of a region I'm looking at, type 1, type 2, type 3. So I think the easiest way to handle this is to project this into the xz plane. So project it this way. You notice the widest portion of this kind of football-shaped region is this circle right in the center. So if I were to cast a light into the xz plane, the shadow it casts will look like this circle in the xz plane. So let's graph that circle, and we'll call that region D. Not a good circle at all, but whatever. We're in the xz plane here, and that's the region D. And what is the radius of this circle? Well, again, if y is equal to 4 here, I can plug, and this is a curve of intersection between these two surfaces. I could plug a 4 into either one of them. If I plugged it in here, I get that the equation for this is x squared plus z squared equals 4. That means it's a circle. There we go. X squared plus z squared equals 4. That means this is a circle of radius 2. So these are 2's. Okay. Now again, because we're talking about a circular region, the best way to approach this is to describe this region in polar coordinates. So in polar coordinates, the region D looks like the set of all r theta such that r is going from 0 to 2. Theta goes from 0 to 2 pi. Okay, so we're going to need that. We're projecting into the xz plane. So what that means is that my my triple integral, when I evaluate it, this guy. Actually, let's wait on that. Let me describe the region E first. So E is going to be the set of all x, y, z, such that. Okay. I keep forgetting to shift my page up and down. E looks like the region containing the set of points x, y, z, such that. Looking here, all of the points, all of the x, z's are going to live in that region D. So I'm going to say such that x, z is in the region D. That means I need to find bounds for my y. Well, y, we already know is bounded by these two surfaces. And to determine which one is the lower bound, which one's the upper bound, look at the surface that we drew. The lower bound should be whichever surface is closest to the xz plane. That's going to give us the smallest y values on those points. That would be the first surface, x squared plus z squared. So x squared plus z squared is less than or equal to y, which would be less than or equal to 8 minus x squared minus z squared here, okay? So that means if I want to evaluate my triple integral over E of dv, that's the formula that we are going to use to find the volume. This can be written as the double integral over d, and then here we're going to integrate with respect to y, where those are our limits of integration. X squared plus z squared, 8 minus x squared minus z squared dv. And then I have a dA out here. All right. Now, because this integral is really simple, it's just dv here. What ends up happening is that the result of this integral just turns out to be the difference of these two bounds. So taking that difference, I'm going to get d, the double integral over d of 8 minus x squared minus another x squared, so that's minus 2x squared, also minus 2z squared dA. Let's go ahead and factor a 2 out of that. So I can say 2 times the double integral over d of 4 minus x squared minus z squared dA. Okay? Now we said before that the region D is better thought of in polar coordinates. So let's set this up as an integral in polar coordinates. This is equal to 2 times, using the limits of integration we found down here. We know theta goes from 0 to 2 pi. R goes from 0 to 2. And then minus x squared minus z squared, because we're working in the xz plane here, r squared is equal to x squared plus z squared. So this will change to 4 minus r squared. dA becomes r dr d theta. Okay? Split this up into two integrals. 2 times the integral from 0 to 2 pi d theta. And then multiplying that r in there, this is going to be the integral from 0 to 2 of 4r minus r cubed dr. Pretty straightforward from here. I get 2 times, this will just be the difference between 2 pi and 0, which is 2 pi. Here, I'm going to integrate, and I get 2r squared minus r to the 4th over 4 from 0 to 2. And then this, after working everything out, multiplying everything together, we're going to get 16 pi for that volume. Okay, and that's going to wrap that up. We have one more example to cover, which we'll do in the next video. That's going to be an application of triple integrals to finding mass and center of mass, just like we did with double integrals. But that's going to be the last thing that we do in 15.6.